A part 1. State the Boyle's law and Charles law. Boyle's law. The pressure of a given constant mass of a gas is inversely proportional to the volume when the temperature remains constant. The volume of a considered mass of an air is inversely proportional to the volume when temperature remains constant. In Charles' law, the volume of a given mass of the gas is directly proportional to its absolute temperature, provided that the pressure remains constant. You have to write in Charles' law, mass and temperature should, Boyle's law, mass and temperature should be constant, pressure inversely proportional to volume. Then write in Charles' law, we have to write that mass and pressure should be constant, volume directly proportional to absolute temperature. It is compulsory to write the absolute temperature. It means Kelvin temperature, not Celsius temperature. In part 2, derive ideal gas equation using above laws. Ideal gas equation. I will consider three situations of a given mass of a gas. For the first situation, pressure P1, V1, T1, PVT, pressure, volume, temperature. For the final situation, P2, V2, T2. I will consider we can use Boyle's law for this situation. To use Boyle's law, we know that mass and temperature should be constant. Then we have to get if the temperature at this point is T, this system is T1. Temperature of this system should be T1, same temperature. To use the Boyle's law. And I will use Charles' law for these two situations. When using Charles' law, pressure should be constant. Then if the pressure at this system is P2, this one also P2, pressure should be constant. We can't decide volume for the this intermediate situation, then I will get it as Vx. Then mass and pressure constant for these two situations. Now I will use Boyle's law for these two situations. P1 V1 equals P2 Vx. It is the first equation. Then we can use Charles' law for these two situations. V1 divided by T1, Vx divided by T1, volume divided by absolute temperature equals V2 divided by T2. It is the second equation. Now there are two equations. We can multiply equations. first equation multiplied by second equation. P1 V1 multiplied by Vx over T1 equals to P2 Vx multiplied by V2 over T2. We can cancel out Vx terms, and then we can get P1 V1 over T1 P1 V1 over T1 equals P2 V2 over T2. Now there are two situations. The term PV over T is constant. Therefore we can get for a given air mass, given mass of a gas, P V over T is constant. We are dividing this PV over T constant for 1 mole is R. R means universal gas constant. Then for 1 mole, PV over T is defined as R. Therefore, for n moles, PV divided by T equals NR. We have to multiply R by N. Then we can subject PV equals nRT. This is the equation we have to get. In part B, a deflated tire of volume V and initial pressure P0 at room temperature TR is connected to a compressed nitrogen gas tank via a valve. The tire initially contains only nitrogen gas. After inflating the tire with nitrogen gas, its final pressure is P, and it contains a total of n number of nitrogen moles. Assume that there is no change in volume of tire. Part 1. Assuming that nitrogen gas inside the tire behaves like an ideal gas, so that number of moles nitrogen gas pumped into tire is n times 1 minus P0 over P. They have given that after inflating the tire with nitrogen gas, its final pressure P and total number of nitrogen moles N. I will consider initial situation. B part 1. PV equals nRT. Then I will subject N, number of moles. PV divided by RT. For the initial situation, I will consider number of moles, nitrogen moles N0. Pressure, initial pressure is given as P0. Volume of tire is V. Volume of tire is not changing with pressure of tire. R is constant. Temperature. Room temperature is given as TR. Then we can use room temperature as the pressure of tire temperature of tire temperature of gas inside the tire. Now, for the final situation, they have given that N0 is a value used to get only the initial situation, but N value is given in the question. N is the final number of moles in gas. Pressure is P, volume V, volume is constant, R constant, temperature is again TR. This is the first equation and this one is the second equation. Now we have to get number of moles of air filled from tank to tire. Then we can get change of number of moles. N minus N naught is the problem. We can get in value PV over RTR minus N naught is this one, P naught V over RTR. Then we can get common factors. Change of number of moles, delta N. V over RTR common, we can write P minus P naught. From second equation, I will subject V over RTR. V over RTR is N divided by P. We can subject from this equation. And we have to substitute to this one. Therefore, delta N equals N over P times P minus P naught. Then delta N equals I will bring P into the bracket. P over P minus P naught over P. Delta N equals N times 1 minus P naught over P. In part 2, obtain an expression for the work done to inflate the tire with nitrogen gas. We know that work done is P times V, PV. Then we have to calculate the change of, PV value, change of PV product. I will consider volume of this delta N, change of number of moles, volume of number of moles, delta N, volume of delta N moles as V dash. Then I will use PV equals nRT, V equals nRT divided by P. V dash equals, in value is delta N, R room temperature divided by pressure of tank, pressure of gas tank. I will consider pressure of container as PC. PC means pressure of nitrogen gas container. We can substitute delta N value by using this equation. N times 1 minus P naught over P RT divided by PC. PC is pressure of container, pressure of gas container. Now we can write work done equals to pressure of gas container into V dash. PV product is the work done. We know that nitrogen gas flows from tank into tire through the valve. Then PV product is the work done. Pressure Pc into, we can substitute V dash in times 1 minus P naught over P RT over Pc. We can cancel out pressure of container. Then we can get work done is nRT times 1 minus P naught over P. This temperature is room temperature. Therefore, we have to use TR for the room temperature. Then part 3, assuming that the pumping process of nitrogen gas is adiabatic, so that the change in temperature of nitrogen gas inside the tire is 2 over 5 times 1 minus P naught over P into TR. The change in internal resistance of an ideal gas is given by delta U equals NCV delta T, where CV is the molar heat capacity at constant volume at delta T, and delta T is the change in temperature. The molar heat capacity of at a constant volume of diatomic gas is 5R over 2, where R is the universal gas constant. We have to get the temperature change. Then we can use first law of thermodynamics. According to first law of thermodynamics, we know that delta Q equals delta U plus delta W. Now it is an adiabatic process. Therefore, delta Q should be 0. Adiabatic means there is no heat flow into gas, so there is no heat flow from gas. Delta Q equals 0. Then we can get minus delta U. This is the decreasement of internal energy. Should be equal to work done. Now we can substitute delta U. They have given that delta U is NCV delta T. NCV delta T. It is the equation they have given. If we are using first value for this side should be minus. Delta W means work done. We can substitute work done by using this equation. nRTR times 1 minus P naught over P. We can cancel out N. They have given that CV. CV means molar heat capacity of at constant temperature. So constant volume. And it is given as 5R over 2. It is depending on number of atoms in gas molecule. 5R over 2. We have to substitute only given values. Delta T equals TR times 1 minus P over P naught. Then we can subject temperature change. Delta T equals 2 over 5 R TR into 1 minus P over P naught. There is a R term in right hand side. This one, when being this R, we have to divide by R. Then we can cancel out R and R. Delta T equals 2TR over 5 into 1 minus P over P naught. It is the given expression. Part 4. The change in temperature increases the pressure temporarily to higher value. So that change in pressure is 2 over 5 times P minus P naught. The change of pressure according to PV equals nRT we can subject pressure nRT divided by V. We can write pressure at tire N R TR plus delta T. Delta T means temperature increasement. This is the new temperature divided by volume. Therefore, we can write nR TR over V plus nR delta T over V. Now we know that nR TR over V is pressure inside the tire, and this part is the pressure increasement. We can get pressure increasement as this value nR delta T over V. Then we can use temperature increasement is this value nR over V times delta T. We can substitute delta T value 2TR over 5 into 1 minus P over P naught. Now we know that this term equals this one. It means pressure inside the tire, initial pressure. 2 over 5 P times 1 minus P over P naught. Now we can get change of pressure is this part. In this equation, there is a pressure change. We have used P naught over P, not P over P naught. P naught over P. Now, we can get change of pressure. Change of pressure is this one. 2 over 5 P into 1 P minus P into this value. We can cancel out P and P naught. Then part C. Gauge pressure is the pressure measured relative to atmospheric pressure. Gauge pressure of a tire is usually expressed in PSI, pound per square inch unit. 1 atm equals 100 kilopascal and 1 PSI equals approximately equals 7 kilopascal. A deflated tire at 20 PSI pressure is pumped further with nitrogen gas to pressure 30 PSI at room temperature 27 degrees Celsius. Part 1, calculate the change in temperature, nitrogen gas in the tire. We can use equation we have obtained to change of temperature. Before using temperature, we have to calculate corresponding pressure PSI value to SI unit. Now, initial pressure P naught is 20 psi. 20 psi means 20 multiplied by 7 kilopascal. 7 into 10 to the power 3 pascal. It is relative to atmospheric pressure. It means 20 psi means 20 into 10 to the power 3 into 7 pascal greater than the atmospheric pressure. Therefore, we have to add atmospheric pressure 100 kilopascal to get the pressure inside the tire. I will use kilopascal values. Plus 100. Then 2 into 7, 14, 140 plus 100, 240 kilopascal. Then we can get final pressure. It should be 30 kilopascals. Relative pressure. It means 30 kilopascals more than atmospheric pressure. 3 into 7, 21, 210 plus 100, 310 kilopascals. Now we can substitute. We have to find the temperature change. Temperature change is 2 Tr divided by 5 times 1 minus P naught over P. 2 times room temperature is 27 degrees Celsius. We have to use Tr in Kelvin. Therefore, we can substitute 300 Kelvin. We have to add 273. Divided by 5. 1 minus P naught is 240. Divided by 310. Then we can simplify and we can get the answer 27 Kelvin. This is the temperature change. It means the difference of temperature. When getting a temperature difference, we can use Kelvin value equals to Kelvin difference equals to Celsius difference. Therefore, we can put unit Kelvin or Celsius. Then part 2, calculate the maximum pressure in the tire due to change in temperature. We can use the pressure increasement. Change of pressure is this one. Therefore, maximum pressure inside the tire. Maximum pressure inside the tire. Initial pressure is the pressure of the tire after pumping nitrogen gas should be 310 kilopascal. But there is a temperature increasement. Therefore, maximum pressure could be 310 plus pressure change due to the temperature change. This one. 205 times T minus P naught. 310 plus 2/5 times P minus P naught. 310 minus 240. 310 plus 205 multiplied by 0, 11 minus 47. We have to divide by 5. 5 divided by 5, 1. 7 divided by 5, 1. 2 remaining. 20 divided by 5, 4. 310 plus 28. 338 kilopascals. Part 3. Usually, this temporary increase in pressure is not observable when pumping nitrogen gas further to deflated tires due to possible reasons for not observing the increase in pressure. We can write usual pumping pressure is pumping process is not adiabatic. Part 3, pumping process. Pumping process is not adiabatic. And we can write another reason. Normal air cannot be considered as an ideal gas. Nitrogen or air is not ideal.